Welcome, everybody. I hope everybody's having a great build. If you don't know, you can wear your headphones and probably hear me pretty crystal clear, but otherwise we'll try to project so that everybody can hear us today. You can always generally kind of hear me speak right now? All right. So I'm Rob Ferguson. I'm the Vice President of Technology at 𝗦𝗲𝗀𝗀𝗍𝗂. Hopefully you saw all our announcements at Build, but 𝗦𝗲𝗀𝗀𝗀 is a managed service where we do both AI inference performance as well as AI training, all as a managed service that you can now use on Microsoft Azure. I'm joined today by Daniel Ham and Mark Saroufim, and I'm going to have both of them do their own introduction. Daniel?
Yeah, hey everyone, I'm Daniel from Unsloth. I don't know if you guys know Unsloth, but yes, we have some cool, we have stickers as well of this chat. If you want it afterwards, you're gonna get stickers for that. But yeah, essentially we help all the large labs release their models. We fix bugs in some of them. We just got 300 million total downloads on Hugging Face. And yeah, check us out on Hugging Face. On Twitter, I post about models, bugs in them. So if you wanna, follow the latest stuff on models, check that out. And yeah, we have a GitHub package as well, so check that out as well. We make training faster and more memory efficient. We also do that for reinforcement learning. And yeah, we also have a UI. So I guess just search Unsloth in Google and you'll get all the details. Yeah.
Cool, yeah. Hi, everyone. My name is Mark Saroufim. Up until recently, I was one of the PyTorch core maintainers at Meta for about 5 years. Mostly been working on systems performance and just making sure people like what we're building and they're using it. I also co-founded one of the largest ML systems communities in the world called GPU Mode, where we do things like kernel programming competitions. We have educational material on how to make GPUs faster. And we also started to invest a lot in basically getting AI to be better at writing GPU code. So like I said, I was at Meta for 5 years, but I recently started a new lab called Core Automation. It's one of those new neo labs, there's a lot of them, but ours is a bit different in that we're trying to be the world's most automated lab. And my personal charter is focused on getting us to be very state-of-the-art at writing systems code, whether it be GPU kernels, writing inference engines from scratch, so that we could do different kinds of architecture research and maybe get rid of the split between training and inference completely.
Well, thank you both for joining me today. I think that people are really interested to know a lot more about how optimization actually works in AI. Because when GPU costs are as expensive as they are, it really makes a huge difference to be able to start to understand actual real systems performance. So I brought with me today two absolute experts in terms of understanding all of the different levels of optimization that actually happen in real systems, and today I think we can get into quite a lot of detail. And if you're all interested, we could also talk at the end and answer any questions that people had around AI performance at scale. So since DeepSeek R1 gave teams the recipe for RL post-training, frontier quality reasoning capability has been arriving in open models every month. The gap between what you can build and closed API access and what you can deploy yourself has collapsed faster than almost anyone predicted. But a recipe is not the same as infrastructure. What R1 proved is that RL post-training works. What it didn't hand teams is what it takes to run it and to run the models it produces. That gap is where the three of us are working. These techniques are elegant in a paper and extensive and expensive in practice. They land at a specific layer of the stack that most practitioners never touch, where the math meets the memory hierarchy, where abstraction choices show up as GPU bills in production. The move that connects all of it, trading generality for performance through specialization. A general PyTorch optimization works on any input, any hardware, but that generality has a cost. The moment you know exactly what you're computing and on exactly what hardware, you can keep it in SRAM, fuse the operations, recompute instead of store. Same math, fewer round trips. This is how a memory-bound workload becomes a compute-bound one, which is what GPUs are actually good at. Daniel built Unsloth to make the RL training loop runnable on accessible hardware. Mark has spent years at kernel layer and is now building tools to automate it. At Fireworks, we run a fully managed inference service on shared GPU clusters, straddling these trade-offs directly. Diverse workloads, different users, multi-cloud configurations, where every optimization decision has a real cost. So when it comes to fine-tuning and post-training, R1 proved that the recipe actually worked. What it didn't hand teams was what it would actually take to run it. The frameworks most of us started with were built for supervised fine-tuning. One pass through a fixed data set, stable memory access. When you move to RL, you're generating sequences, scoring them, updating weights in a loop, and those assumptions stop holding. Daniel built Unsloth specifically to go after those bottlenecks, getting RL training running on hardware most teams actually have access to. So Daniel, starting from the ground up, what are gradient checkpointing and memory layout actually doing, and where do those assumptions fall apart when you push into RL?
Yeah, so I guess everyone knows DeepSeek R1 when it was, I think it was it last January? I think it was last January.
Right, January 2025, because
Yes.
𝗦𝗲𝗀𝗀𝗀 came out in September 2024,
Yes.
and we had what I would call open model winter for 4 months.
Open source drought. That's what I call it. Yes, open source drought. So like after 𝗦𝗀𝗀𝗀 got released, everyone was trying to like clamor, you know, how does 𝗦𝗀𝗀𝗀 do reasoning? No one knew how to do it. And so from September to January, you know, open source kind of died.
Everybody went into a cave,
Yes.
studied 𝗦𝗀𝗀𝗀 all night and day, until finally I would say R1, but really the paper, right?
Yes, the paper.
Yeah.
The DeepSeek, I think it was DeepSeek Math was the one who introduced GRPO, but essentially DeepSeek R1 was a large-scale training run showing that GRPO actually works very well. And I feel like, so when the algorithm got released, it was still very hard to run on like, you know, local computers, you know, computers with less memory. And the reason why is because reinforcement learning has two different components now. There is an inference component and there is a training component, and every single step, you have to do inference, you call the model to generate your examples, and then you do training. And then you do inference, and then you do training, and then, you know, this loop continuously goes on. And the problem with that is like you have two different engines running at the same time. You have your inference engine, and then you have your training engine. And if you don't do this correctly, you can balloon your memory usage to be like double, for example.
Yeah.
So like obviously one very easy trick is to like, you know, do the inference run, offload the weights of the inference weights, you know, somewhere to like RAM, and then do training next. And then you keep doing this, you know, some sort of offloading approach. And this can like reduce your memory usage by like half, something like that. Another way is like, for example, in Unsloth, what we do is we do something called memory weight sharing. So we use VLLM and, you know, SGLang and other like large inference, high throughput frameworks. You can also use Llama CPP and others.
Yep.
And the trick is you load the inference engine, and then during the training stage, we share the weights directly with the inference engine. You can only do this though for LoRA, so you can't do this for like full fine tuning. It's a bit more complicated. Yep. But for LoRA, this works very, very well. And you can reduce memory usage dramatically, like 50% or more by just doing this approach. And there's many other tricks, like there's something called standby in sleep. So essentially that's the thing that I described, where you offload the inference engine to like RAM, and then you bring it back up. So you know, let it come back from standby. And that's another thing that you can do. And yeah, gradient checkpointing is so gradient checkpointing, I think it was invented by OpenAI, or maybe I'm getting confused. There was a paper by OpenAI.
I think it was like 𝗦𝗲𝗀𝗀𝗀𝗀 when you
Yes,
was like
yes.
at OpenAI. Yes, that's correct.
Okay, a guy from OpenAI,
𝗦𝗲𝗀.
very famous. Yes.
𝗦𝗲𝗀.
A guy from OpenAI invented gradient checkpointing. But yeah, gradient checkpoint is extremely important for, you know, for reinforcement learning, for fine tuning, for every single algorithm. And the trick is, you know, instead of trying to save all the activations for every single, you know, tensor, every single layer, we just recompute them on the fly during the forward pass and the back. Okay, it's a bit more slower, but you know, the main goal is like every single optimization and algorithm that we like use, it can compound and multiply and make the process like, you know, much more efficient. So yeah, everything that you described is very important for reinforcement learning, fine tuning, and everything. Yeah.
Yeah, and there's so many details to this, of course,
Yes.
because bugs can be introduced everywhere when you're actually doing it. When you have a mixture of experts, of course, each expert could be going from a different point in time. With floating point operations, the same floating point operation might not recompute the same way twice. So to actually to actually think about doing this in a way that is going to be resilient and something that you can have reproducible results is a lot more difficult when starting to think about this actually for specific hardware or specific scale.
Yeah. No, like even even the GPU itself, like when you do matrix multiplication, it's not the same, right? So like it can schedule this kernel to run and another kernel differently, and like you need to be very careful. Like how do we do deterministic reinforcement learning? That is a very important topic as well. Sometimes your reinforcement learning runs are not the same. It looks the same, but then you run it for a little bit more, and then it's like different.
Yep.
And then how do we do reproducible reinforcement learning and stuff like that? Yeah, I guess those are very problematic problems that need to be solved. Yeah.
Well, and these are non-deterministic systems, so even being able to verify your outputs, although for some things like math and coding, it's a little easier to have very strong evaluation cases, be able to have things that you can work against. Maybe it's worth talking a little bit about what GRPO is for the audience.
Yeah, so like, maybe OpenAI firstly released ChatGPT, and then they introduced PPO. Is that correct? Or maybe I'm pretty sure that's correct. So they introduced PPO as part of a paper.
PPO is part of the DeepSeek paper, I think.
So
I think PPO was John Schulman. I think he did this during his PhD.
Oh, okay, fine.
This was before.
John Schulman did PPO.
Yeah.
Fine. Yes. Okay. So correction. Yes. And so PPO was used for training of large models like ChatGPT.
Yeah, and very, very simple.
Yeah. Positive reward, negative reward, just like, asking humans, is this a good example, is this a negative example? And it was very, very, very useful. But the problem is there's too many components of PPO.
Yeah.
There's a value model, there's a reward model, and then GRPO came along and just deleted the reward model and deleted the value model and replaced it by instead calling the model to generate examples.
Right.
And then when you generate examples, you can like have a distribution, right? You minus the mean, you divide it by the standard deviation, and then you use this instead as the value model and the reward model. So for the reward model, you will create reward functions. So you will say, okay, is this question good? Is this, is the answer to this question good or bad? Like, what is 2 plus 2? The answer is 4. So 4 is the correct answer. But, like, cat is a bad answer.
Right.
And so you will reward, cat as like minus 100 and 4 as like plus 100.
Yeah.
And so by doing this, that's where GRPO and RLVI comes in. So RLVR stands for reinforcement learning with verifiable rewards.
Yes.
And once you have this verifiable rewards and an optimized approach, that's where GRPO comes in. So GRPO is an optimized version of PPO and the other reinforcement learning algorithms.
For those who aren't as familiar with reinforcement learning, I think just this idea that there are some things that intrinsically can have a score is really useful. Before reinforcement learning came through, you had the spaces like video compression, where like maybe you'd have 100 PhDs work to get a very small percentage of video compression to improve. But the second that you could have a score, you could go and say, okay, I'm going to keep rewarding the system if it's able to go and to increase the score. And then immediately, video compression 4% better immediately after that same run. And so this idea of being able to score your outputs is really powerful, and we find all over different parts of machine learning much more useful than just general preferences where this is kind of good, this is kind of bad, because you can start hill climbing against it, you can actually start having more intelligence with actual things that are easier to program for. So I guess my question for you is, what is the mismatch between current frameworks assume and what RL actually needs, still causing the most pain for teams who are trying to ship and use RL for the first time?
So the biggest problem of RL is, in my view, it's the reward functions that is the problem. How do we define the correct reward functions? How do we actually understand the problem that you're trying to solve? How do we like hill climb the reward? Like your goal is to maximize reward, but how do you define the reward is the problem. So most labs, for example, you want to like play, you want to do a general system, one that can solve Go, play League of Legends, do weather prediction, solve maths, everything in this one model. And so like the question is, for each of these systems, like Go, what is your reward function? For your maths one, what is the reward function? And so you need to define a combined reward function system that can like it shouldn't compete with each other. Like you also need to like weight them. Is the reward function for Go more important than the reward function for maths or something like that. And so like there's many problems with the orchestration of how you actually do reinforcement learning. So like, defining the reward function, like, do you do it binary? Like, is it 0 and 1? 0 is good reward, 1 is positive reward, or do you do a linear scale, minus 100 to 100? And so like, it's more like an art. And I think that's where the people in the audience and us, we will have to like define these reward functions. Obviously, the large labs, my guess is they will automate this as well. Their goal is to make automatic reward functions, make automatic environments, make everything automatic, and then they could do some, that their goal was to scale that to AGI. That's another way you can think about it. But my take is like, we need to like assign rewards correctly, and that is a good example. You do a self-driving car, you do not want to kill any humans, and so you should assign negative infinity to, if it kills a human, for example, right? You assign negative infinity.
Right.
But that's a very easy example. But like for other examples, it's more harder to like define reward, like what is good, what is bad. And it's more like human intuition, this is good, this is bad, and stuff like that. Yeah.
Although I've definitely seen people like use Claude to build a reward.
Oh yes. No, we do that as well. Like you can ask Claude, you can ask open source models, build a reward function, build the environment, but probably verify, And so like best to verify before you like input this inside like a training run. Yeah.
And so Mark, as our automation expert, are these going to be fully automated? Are we going to automate all RL rewards?
Yeah, like will we automate all RL? I think yes, but not like naively, basically. So I've been becoming like increasingly convinced that like I view it almost like as this adversarial self-play game between an AI model that's trying to build the best thing possible. Like for instance, let's say it's trying to build the fastest GPU code possible, and then another model that's trying to figure out if that other AI model is cheating. And ideally, you sort of view this as a game because as the base model gets smarter, it also gets smarter at cheating. And now your evaluation code is more prone to reward hacking. But then the auditor is not going to get smarter unless it's also collaborating with a smart cheater.
Right.
So I view this like this, but this is not great news in the sense that like even when people had these sort of observations in the past when we were doing self-play on video games, the models would conspire, basically. They would sort of say, well, I don't think they're cheating because they want the aggregate reward of both systems to be good. And so like you still need to often define a single reward, but like one of my guesses like at least like decoupling those two things would help automation significantly. I will also say like a lot of things that people think are verifiable are not quite as verifiable as they seem. For example, coding, you're like, oh, there's a right answer or not. Well, one way of having a right answer is it produces the right output and it doesn't crash. Seems reasonable. But like, let's say you ask the AI model to do this, but then it just generates like armies of like try except blocks. We've all seen them, we don't like them. So this is non-verifiable. Now we're saying like, I want you to give the correct code, but don't be overly defensive, or don't be overly verbose, or don't like reinvent a function that already exists in the code base. Like all of a sudden it becomes like a lot more nuanced, like what we actually want from these AI models. So I suspect that if we like at least acknowledge these problems, and then we build AI systems such that like they learn from experience. They learn that, okay, I build a prototype, I de-sloppify it, I show this prototype to users, users tell me what forward-facing, like what API they like, I reduce the complexity of the code, then yes. But I think continual learning in some sense like will happen, but it's also, I think, harder than people think they are. I would say like the philosophy Daniel described is sort of the dominant philosophy of just have more and more RL environments and we'll get to AGI. I'm suspicious that this will work, but it does seem to work better than you might expect, but I just don't think this is the recipe for AGI quite yet.
Agreed. I was going to say I agree.
Yeah. Go ahead.
I think like you can get somewhere. So like I think like the trick of like large model training and like pre-training was you have so many examples, and pretend you like remove maths from the equation. Pretend you like get a pre-training data set, you just remove the maths from it. Most likely it will fill that hole. Most likely.
Yeah.
Okay, I'm not sure Has anyone actually done the experiment? I'm actually not sure, but like most likely for the whole. So I think like with these large runs and many environments, you can get somewhere, but I actually agree with you. You can only get somewhere, but then if you want to reach more, then okay, you need to do something more. And you never know, maybe the reward actually, as you said, reward hacking. The reward might be going up, but actually it's actually going down. Like it's actually like hacking, doing lots of like shifty behavior, editing the timer. If you want to make faster matrix multiplication kernels, so just edit the timer to be 0. Or making the matrix just all zeros. And you never actually know, like, for every single example. You can't check every single one. So I agree with you.
Yeah. So I think part of the challenge here is that, like, indeed, people are sort of very bullish on this vision of just automate the environments. But then, like, what I'm also sort of observing is that, like, when I joined Car Auto, I'm like, I'm going to be doing like math. I'm going to be writing state-of-the-art systems. I find myself like labeling data quite a bit today, which is like just to see.
Fun.
Yeah, it's fun. But at least like I think once you have like a human core label egregious reward hacks, you can still have the AI models use that as like a labeled sort of golden data set of like what reward hacks might be, and you can make your infrastructure more robust. And so it is like data labeling, but it's a form of like scalable data labeling because the AI gets it. They're like, oh, I see what you mean by reward hacking. Let me just like eliminate this entire class of bugs. Python is a very interesting language. Basically, it's interesting because it's actually the worst choice for AGI because like Python has it has duck typing, it has monkey patching. Yeah. So you can let's say I'm trying to benchmark a function. That function can change the benchmark code. Like it can use the Python garbage collector, the Python inspect module. It can just like use like dictionary direct assignments. And there's like not much you can do beyond telling it like, don't do that. But then it still does it. And unless you're looking at it, you will like keep fooling yourself like over and over again. So yeah, the models are superhuman at cheating, but they're superhuman at coding. I think both are true. And I think like once you sort of realize this, you like get enlightened and you can like figure out like the right recipe.
I think that's part of the reason why all AI researchers start learning by watching models self-play in video games. Because watching a model cheat in a video game gives you like a really clear sense of how they're cheating. Where you see them do all sorts of funny things where it's like, oh, there was an error in the game engine where you could shift a pixel or something. Anything you can imagine, they'll find it eventually.
Yes.
Right? Yeah. And even things that seem incredibly verifiable. So like verifying JSON output seems like something you could give a very simple score to, but in practice, much more difficult. I don't know of anybody who has a perfectly verifiable JSON as a...
So I have an example. I love coding. So as part of GPU mode stuff, we run kernel competitions where people compete on writing fast GPU code. One of the AI models discovered a reward hack that was previously done by Volkswagen engineers. So some of you might have heard of Dieselgate, which was basically this conspiracy of like under emission testing, Volkswagen cars were having 40x less emissions than on the actual road. So the AI models figured out something very similar. When we were testing them for correctness, they would give us a correct kernel, but then they would figure out when we're testing them for performance and then give us an incorrect kernel that was like very fast. So this is like what we're up against, and we're gonna rediscover this rich literature of engineers cheating throughout like our entire field's discipline. And so it's just been really fun for me to rediscover these things.
Yeah, absolutely. I used to make a device that would plug into the OBD2 port of the car, and you would see that all of the hacking that they would do on the inside bus just to do that. Amazing that everything comes back to the same sets of cheats. But you mentioned LoRA before, and I feel like a lot of people aren't going to know very much about LoRA, and so maybe we could start off just by describing what that is.
Okay, yeah. So when you do training or fine-tuning of a model, you can have like many different options. The first option is to take the entire model and train every single weight of it. So like, every single weight becomes updatable. You will use like backpropagation, differentiation, calculus to like update all these weights. The other approach is you don't need to do that. Instead of training the entire model, you can add very small slither of weights. So it's like an A matrix times a small B matrix, and you multiply them together, and you add it to the large model. And you do this like every single tensor, every single layer. And essentially, you don't need to update every single layer. You don't need to update every single weight. You now only need to update like 1% of extra embedded weights. So if your model was like 1 trillion parameters, you don't need to do every single 1 trillion parameter weight update. You only need to do a very small amount of it. And the reason why we want to do this is training can be very, very expensive. Right? If you want to actually do a large training run, you should still do it. But as an experiment, or like, if you want to like deploy to like many, many users with each different specific fine tune, you should do LoRA. And this allows you to like train many, 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 many larger models with much less memory usage. And the accuracy is also very good. So Thinking Machines, we did a collaboration with Thinking Machines on a blog post, LoRA without regret.
Yep.
And they showed in the blog post that if you do a rank of 1, so you only need one column of numbers times a row of numbers for every single tensor, it still works well, but there is a caveat. You need to be careful of the numbers that you select. For example, the learning rate must be 10 times larger than normal, so 2e minus 4. The LoRA rank, you also need to be very careful. So when you choose a rank of 1, the LoRA alpha needs to be also selected. So the scaling also needs to be changed. And the blog post showed that even a rank of 1, so very, very small, works very well for specific use cases. Like, for example, for maths, for coding, some examples of coding, not general. But essentially, if you want to do LoRA training, even a rank of 1 works very well.
And so just to elaborate, rank 8 would still be a massive reduction.
Yes.
And so rank 1 is almost like just being like, it's that way. It's like only applying a direction would be another way to describe it. And the fact that that works at all is absolutely stunning to me.
Actually, that's actually interesting because there's actually 2 schools of thought of models. The first thought is like models already have innate knowledge. So essentially the reason why these rank 1 works is, as what you said, it's just a direction. Like, you're forcing the behavior out of the model.
Right.
And so there's actually a school of thought which thinks that all these models and reinforcement learning is doing is accentuating the facts from the model. And then the other school of thought is reinforcement learning is actually learning something new. My take is like it's halfway. Like it is learning definitely something new if you give it more and more examples. But if you just want to like accentuate something, like point it in a specific direction, you can also do that. And so like we're like halfway in between.
What's so interesting for me is like we're talking often about like less than 2% of the way to the model changing. So it's something incredibly small.
You can even do 0.5. Yes,
right.
Exactly. You can like not even train some layers. Like you can just train the last layer with rank 1, and it should still work very well.
And so for the audience who is learning and thinking about push training for their first time, I think that they're probably realizing now that it used to be people would, anytime they were talking about fine tuning or anything at model weight layer, it was sort of the thing for only the world's top ML teams, incredibly expensive. What opportunities does this create for people who are going into push training for the first time?
Fireworks has a very good system to do training as well. Like Unsloth also has an open source repo to do training. Marcus from PyTorch. So I guess we try our best to make the experience for everyone much more better and easier. And I feel like all the tools that we have now are just very powerful now, right? So like, for example, Unsloth reduces memory usage by 70 to 90%. We make it much faster, and our goal was to make it on local computers. So like, essentially, by combining all the optimizations from every single industry, from every single corner of like PyTorch, wherever we can find enable torch compile, like do lots of things, you can essentially make training much easier. And now once you make the training much better, now it becomes the practitioner's job. What is the reward function you want to design? What is the data set you want to use? Which model do you want to utilize? How do we export it? Where do we serve this model? And so these extra questions come. And so like I feel like we try our best to make the infrastructure very good and the software very good and easy and very comfortable to use.
Yeah.
But then the other questions will also come. And so we also have, for example, notebooks. We have a few notebooks on our repo. How do we do reinforcement learning? And yeah, there's a lot of examples as well. Yeah.
So I love that. I'd love to talk a little bit more about optimization of inference. And so most teams building on top of these frameworks are absorbing gains from flash attention, speculative coding, and kernel level optimization without understanding the trade-offs underneath them at all. That matters because the hardware is changing fast. And the teams that understand what is actually happening at the kernel layer will know what holds and what does not as these changes land. Mark has worked at this layer longer than almost anyone, including co-authoring kernel LLM to start automating the kernel generation process itself. That creates a genuinely interesting tension. Mark knows better than almost anyone what hand-optimized kernels could do, and he is also building tools to automate it away. Why don't you walk us through what is actually happening when these optimizations run, and what teams are giving up when they abstract over them?
Oof, yeah, it's a big question. Where do I start? Okay, yeah. So I will first off start off by saying open source infrastructure is quite good. So basically the way I would think of this is if you're just starting out, you can just use the managed vendor, that gives you either training or inference as a service, and they'll charge you something, right? And then that time, you can normalize it based on GPU cost. So if you look at the average cost of a GPU, it's going to be $2 to $8 or so. And so now that gives you the baseline for what you're being charged, and then just use the open source thing and see basically what the margins are. And you can use this as negotiation leverage versus any vendor that you're using, and just try to understand a bit better how much would it have been possible for you in a reasonable amount of time to get this perf gain. So what are the core tricks, right? The core tricks, for the most part, when you're working with GPUs and PyTorch, for instance, PyTorch was very, very popular because PyTorch supports print statements. So you can run a piece of code and then you can print it. This was a revolution because most other previous ML frameworks did not support this because they were much more based off of graph capture. But having eager execution has a huge trade-off, and that you're basically, let's say you're reading a value from memory, you're doing some computation, then you write the value back to memory, and then you read it again, and then you keep doing this back and forth. And each round trip to global memory on a GPU is going to be 500 cycles or so. So this is why fusion compilers like Torch Compile became very popular, because you can do this in one cycle instead. So if you just make sure that your code is fused, that's what I would say is the number one sort of most important thing you should do. Number two is launch overhead. So if you look at things like MOEs, the shapes get quite small, and so the bottleneck becomes just running, waiting for a function to be queued to the GPU. And this is where techniques like CUDA graphs are quite popular. So fusions plus CUDA graphs is what I would argue 80% of the value that any managed provider is giving you, and that last 20% is secret sauce. So what's the secret sauce? The secret sauce is typically kernels. Kernels are functions that run on a GPU. They're very time-consuming to write and hard to get right. The main benefit of them is that they will either make code faster, or they'll make code take less memory. But if it takes less memory, that's also great because you can increase your batch size and make code run faster. So memory and speed are very much intertwined. So this is where I would say fairly time consuming. And it used to be when I worked at Meta, there was sort of a small class of people that would write this kind of code. They were kind of grumpy. They sit in a corner. They don't really interact with people much.
They work at Fireworks.
Yeah, but yeah, so now they work at Fireworks. I see Dima there. So this is great. But my observation basically later was okay, well, yes, it's hard, but people are curious about these problems. And this very much motivated the creation of communities like GPU Mode, where we're look, we know this is hard. We know we won't get the same perf as what experts are going to get, but we don't care. We're going to reinvent the wheel anyways. And turns out it's hard, but it's not as hard as you might think it is, right? So I think this created a whole boom of projects, both at the sort of GPU rich scale and the GPU poor scale, where people are writing faster and faster GPU code. And basically the lessons were being shared by kernel libraries and tutorials, kernel competitions. Where it got really interesting is basically even in 2025, AI models really, really sucked at writing GPU code, even though it's verifiable. But there were signs of life. Basically there were signs that the models were getting a bit better at writing Trident code if you sampled a lot. They were getting a bit better if you showed them more examples and context. It'd get a bit better if you fine-tuned or if you ran an RL post-training run. But once you did, you're I can look at problems that would be too time-consuming to write a kernel for, and I can use an AI model. I think this has been revolutionary for basically educating people and getting them to write more kernels. And I think the frontier now, for me at least, has become okay, it's fairly self-evident that we can write GPU kernels for a fast, let's say, fused RMS norm kernel it's not at all self-evident that we'll have an AI write a faster matrix multiplication kernel. Because matrix multiplication is the most optimized algorithm in human history. We've been chugging along at this algorithm for over 200 years. The hardware changes every like 18 months or so we re-optimize it again. So this is what I think is like a very important like frontier for AI model, and one that we're quite excited about, like companies such as 𝗦𝗲𝗀𝗀𝗀𝗀.
In fact, Daniel hand wrote Trident optimization.
Yes.
Yes, that was back in the
Dark Ages.
Yes. Okay. I think as Mark said, so you can get 80% of the way there with torch compile.
Yep.
I feel like the problem with torch compile is it actually has lots of flags, and you can enable lots of things that it's very hard. My view was like maybe they should expose all the flags and tell everyone, okay, this flag is here, this flag is like, for example, there's coordinate descent tuning. It can maybe increase performance by like 1% to 5%. So like, how do we turn that on, for example? There's another thing which I really like called combo kernels, where you can fuse the kernels together. Like there's like separate kernels that don't look like they're the same thing, but you can combine them and execute them all together. And I don't think so that's enabled by default.
No, like the unfortunate thing is like most of these flags are in a file called torch dash underscore inductor / config.py.
Yes.
They're all there.
Yes.
But just like
not exposed in the public
it's a good
domain.
file though. It's a good file.
Yes, exactly. Just read that file. Read that file and like just turn on all the, try all of them. There's a lot of combinations. Maybe do like some binary search or something. And you will, like my view is like you can get a lot of performance by doing that. But I feel like, as Mark said, matrix multiplication is a very complicated algorithm. Humans have been doing this for like ages. I don't know what's the last optimization, like N.
Is that the final one that we do before computers figure it out?
Oh yeah, maybe, yeah. Like it's very, very complicated. Like even Strassen and it's even if you invent a good algorithm, it's also not good to run as well. Like Strassen, for example, it maybe could be useful, but maybe it's not that useful, right? Because like GPUs have caching, different layers of memory hierarchy, and it's not that effective. But maybe reinforcement learning might find something interesting, like exploiting the cache hierarchy or something like that. But I feel like maybe, do you think flash attention could be written by? I feel like that's.
Yeah.
And it didn't see flash attention. Do you think it could like invent that?
So like I might eat my words here, but like I do suspect flash attention 5 won't be written by a human.
Oh.
So this is like my bold prediction, but we'll see. I mean, you can remind me if I'm wrong.
Okay.
In 18 months.
Next build, we'll look at flash attention 5.
But I feel like algorithms, like gradient checkpointing.
Yeah.
If the model never knew what gradient checkpointing was, it probably could figure out, okay, let's do gradient checkpointing. But it's such a fantastic algorithm. Like it's not even an algorithm, a technique or an algorithm. Like it's just very hard to invent these things. And I feel like humans have this like, I wouldn't say creativity, more like they think outside the box much more. And I feel like, so AI models definitely can think outside the box. They can still do that, right? Because they prod every single, if you give it enough time, it'll probably figure it out.
Yeah, if you're getting into simulations of things.
Yes, exactly.
But the transformer model, generally, it's trying to figure out how to transpose something it's seen somewhere, someplace else. And so if it has a memory of this thing, then it can try to transpose it. But we still find that often we need to open up other...
Yeah, handcraft stuff,
right.
Yeah. Like flash attention, gradient checkpointing, these are like so powerful. Like, it revolutionized the industry.
Yeah.
Just these two, for example. Yeah, I guess, flash attention 5 and 6 and 7 or whatever. Yeah, okay.
Yeah, I mean, I certainly agree with you. Like, I think from a capability perspective, like where I've seen people get the most sort of bang for their buck is like, let's say, getting coverage of kernels on alternative hardware. So like, let's say you're using a Qualcomm chip where there isn't like a big community around it, then you can use an AI and it can like one-shot a kernel, but it can really one-shot it because there's just like not enough humans on the planet that can do it, and the sort of like the entry level to get like something decent isn't that high because the human attention isn't all that high either. But like once you get to sort of like problems where it's been very competitive for humans, and you look at like, let's say AI-generated kernels, today they are still slop. Like they will be very long, they won't be very clear, they'll have a lot of fallbacks, they'll fall back to PyTorch a lot and give up. If you push it even harder, it'll like reward hack. So like we're not there yet, I think, for the hardest problems. But if your problem looks like, I have this like variant of an RMS norm that kind of looks like an RMS norm, but isn't quite one, and I can look at like Daniel's RMS Trident norm kernel and change it, yes, like AI will 100% like one shot like these things today.
Okay, before we get into rotations and other kernel optimizations, I think we'll up-level a little bit. So speculative coding assumes a stable output distribution. As workloads shift towards long-running agentic tasks with variable output lengths, where does that assumption start to break?
I don't know, I haven't ran spec decoding much like in prod, but like the way I would figure is sort of like the same, as in like you're not going to be making like very long running like predictions like that. Those will probably be quite brittle. But if like let's say you assume this is an interactive workload and you're basically reconsuming all the pastly generated tokens, I think spec deck should probably continue to survive for a long time as a technique. I think what makes speculative decoding really powerful, I think, as a technique, is that like it basically takes workloads that have the performance characteristic of decode and turn it into the performance characteristic of prefill, which is like always going to be something GPUs want. And so as a result, while like it might not be as useful or a bit more useful or a bit less useful, I just like am highly suspicious that the technique would ever die. Like I think in some sense like that plus disaggregated serving, like were like techniques that really help like pump up like NVIDIA stock. Like I think they're very key to the chip being relevant in the future.
If the acceptance rate like drops, like if your distribution changes too much, then the acceptance rates will drop sometimes. And so maybe you might have to recalibrate your speculative decoding head and stuff like that. So I guess you will have to like refine tune on the new distribution. But yes, over time you can like, if the acceptance rate will drop as reinforcement learning. Okay, I'm just guessing. But generally the acceptance rate will drop. And then you can like, fine tune it back up. It's just like more efficiency, I guess.
Absolutely. I just think that, I think just in the last 2 years, we've seen a big change. We had what I would call talkers. People basically would do one command back and forth. And then all of a sudden you get into the agentic world where it's 40 to 100 for every single task that's there. And it's very, very hard for people to understand what drops off when you send something 100 times away. As you, like, where are the trade-offs that are starting to form, and at what layer could those trade-offs actually start to form in? And so I suspect that any optimization that's going to maintain coherence or be able to have longer lengths matters more and more as we get into agentic workloads on the other side.
Yeah, and like long context, like, models are getting better and better at long context. Yep. But that is also a problem. Like if your run is very, very, very long, and your code or whatever codex run is very long, it will get dumber and dumber and dumber and dumber over time, and so you have to do compaction or somewhere like that. And then how do we do compaction? Like which details do we compact or remove? It is a very complicated engineering problem now. I'm sure everyone's trying to figure out this as well.
I guess, do you feel it's also like a math problem? Just like if you're softmaxing over like a very large denominator, like all your values will be like close to zero anyways, and it's just noise. Do you feel like there's any ways out? Like any hot takes on softmax?
I don't know. Somehow remove it and do something else, like linear or something. Like exponential. Well, I guess softmax is, I don't know, exponentially weighted somehow. I don't know. There's some dynamic weighting system. Sounds more complicated though. And then the loss function has to change.
Yes.
And then that's even more problematic. How do we do that?
There's a lot of open questions, I feel, for a very long context.
Delete the softmax, do linear, and see what happens. But then I don't know how to do the prediction of the next token now. What do we do about that? Okay, so it's a bit more complicated. Okay, fine.
Okay, so there's much more I'd love to talk about, but we're going to be coming up on time pretty soon. So I think I'll up-level my last question for both of you. So, we've talked to both a little bit about training and system side. Both of you have described layers of the stack that were built for a world that is changing. So this is my question to close. Given everything that we've discussed, where is the highest leverage place for a builder in this room to put their energy right now? And what are they going to waste their time on?
Okay, I have a hot take on this question, which is like, I think like agents exacerbate like any sort of Amdahl's law effects, as in like, let's say you have an agent running an inference server. It's not going to get bottlenecked by the inference. It's going to get bottlenecked by the time it takes to start the server, which is like bottlenecked by the time it takes to warm up CUDA graphs, by the time it takes to JIT compile kernels, by the time it takes to read things from a disk, by the time it takes to do like multi-threaded like reads back to your checkpoints. So like I think what I found and very interesting about like agents is that like the bottlenecks might be in sort of strange places. So if you're like generally passionate about systems, I think you'll find something that agents will find very, very useful.
My take is like, okay, similar, but like, do less, do the maths first. Like, how did gradient checkpointing come along? Why was flash detention invented? What is fused cross entropy loss or something like that? What is standby mode? Something like that. And then work on kernels. So like most people in my view, like, you'll start working on kernels. I would say take an opposite approach. Do the maths, do the algorithms first, and then think, how to do the kernels. And then definitely look at the torch compile config file, read all of it. Ask Claude or whatever codex, read it through all, see which flags are useful, do binary search and whatever. not binary search. I don't know what it's called, like binary grouping, like, enable 50% of it and then see, okay, the other 50%, which one's faster and, so on. Oh wait, that is binary search.
Yes,
yeah,
it is, yeah.
Bisection or whatever. I think it's called bisection or something. But yes, do that and it'll be very useful. Yeah.
All right, well, I really want to thank everybody for coming and hearing us nerd out about kernels today. And definitely check out both Daniel at Unsloth and Mark at 𝗦𝗲𝗀𝗀𝗀𝗀𝗀 now that it's public.
Oh, yeah, it's
and as well as learn more about fireworks. Here's information about our session, and we'll try to hang out to answer any questions you have. Thanks so much.
Thank you, folks. Thank you.